let's get started. I'd like to review this page. I made some minor mistake, and it has a lot of information, so it's better to review this. Okay, go through again. First, this technique is specially developed to determine root of this special shape of type of equation has any RHP root. Okay, that is a purely mathematical thing, probably, or not. I don't know. Okay, but somehow we are using this mathematical result to determine stability of closed loop system, any closed loop system. For example, this PWM converter. So in this equation, TMS actually can be any equation, but this case we call it, or we assume this is a loop gain of some feedback system, and 1 plus TMS equals 0 is called characteristic equation. Root of this equation, this characteristic equation, is called system poles, natural mode, or eigenvalues. They are the same terminology, okay, for different implication. All right. So characteristic equation is this one. Assume this TMS is given by this. This is time constant form, but it's better to use another form. So I need to modify here. Sorry for this. Maybe I select this one. No. I need to change color here. Right. Okay. Delete this and use omega m for arbitrary number, constant. So this is a pole zero form. So this form is maybe convenient for this polar plot, to plot this polar plot. But for the frequency responses, we are using different form, and that form is this one. So, I want to have what happened? Something has been changed. All right. Okay. Omega m prime divided by s, and 1 plus s divided by omega p1. Another first order term, s plus omega p2. Okay. So this is the standard form you are using for the frequency response plot. Okay. So this is more convenient. And the loop, the Bode plot of this one, asymptotic plot of this one, is shown in this purple color. So initially we have integrator. So, and in integrator gain is omega m prime. So if you extend this line to meet this 0 dB line, that frequency is omega m prime. Okay. So initially it start out this minus 1 slope, and it hit this omega p1, and the slope will be changed to -2, and it has another pole, omega p2. Then slope will be changed to -3 slope, and the phase characteristic is shown here because the initial slope is -1. The initial phase is -90 degree, and the phase will decrease, and eventually it will arrive at -270 degree. Okay, that's obvious. And in the middle, there is some line or frequency where the phase falls to -180. So that is this one. And usually we call it this frequency omega c or omega c prime. Omega c is fine. Okay, so this is the Bode plot of this transfer function, and let me delete this. This is not informative. Okay, so what I wanted to emphasize is you are interested in this equation, okay, whether this equation has any RHP poles, but you are using only Tm, okay, not 1 plus Tm. There is the one advantage of Nyquist analysis, okay. So Tm is here, then draw the polar plot here, so we will do that later. So this is S-plane, and there is another S-plane, so maybe same S-plane or different S-plane, maybe different S-planes. There are two S-planes, and this is the one S-plane. This is sigma j omega. So we want to have any pole in the right half plane of S-plane. For example, here is one pole. This is the real pole, and this is the complex pole, which appears as the complex conjugate pair. Okay. So for this case, we have three RHP zeros, or RHP poles, or unstable eigenvalues, or unstable natural modus. Okay. So to test this, we perform the mapping. Okay. So this is S variable. So here S is simply S is sigma plus j omega, and there is another plane for this. The axis is different. This is u and this is the jv. Okay, two different planes. So you walk around this along this line, this positive imaginary axis, and go around here, and the radius of this thing is infinity. Okay, so it covers the entire RHP of S-plane, and come back this plane and follow this and avoid this point, this origin. This is the singular point. So because this equation has pole at the origin, this is the singular point. So we should avoid this to use Cauchy's theorem. So Cauchy's theorem will break down if we pass this kind of point. So you are traveling this, and arrive here, and going back to the original, and detour this, and come back to the original point. During this period, we evaluate this along this line. So in this line, S equals j omega. So you replace S with j omega, and evaluate this in polar form. Okay, that is very complicated, or not convenient, but we already have this Bode plot can be transferred to the polar plot easily, because this is evaluated by replacing this S with j omega. Okay, so we have the result at low frequencies. Okay, there. Okay, this is real imaginary axis, and this axis is the real frequency. The frequency we are talking about all the time, sinusoidal response. So at very low frequency, magnitude is very large, and the phase is minus 80 degrees. So it starts out some point way below this, but we draw that point here, and it goes around this. Okay, assume this is true. Okay, because this order is 3, and order in the numerator is 0. So final phase will be minus 270 degrees, and this line will slide along this real imaginary axis. Okay, that is obvious. Okay, and you are here, then you need to go around this. Okay, long path with infinity radius. But this is very easy, because S is here. If this radius becomes large, then S becomes very large. Then whole thing becomes 0. Okay, so this whole line, okay, encompassing the entire RHP is this point. Okay, you start out this point, and you are here, and you stay here for a while. Okay, and follow this. This is negative imaginary axis, means minus frequency is not existing in our world, but mathematically it is okay. Okay, so you should consider this. Then this part is j omega. This part is minus j omega. That means the polar plot of this has this imaginary axis will be changed in sign. That means this part is mirror image of this part. Okay, so you just flip this part to this. Okay, then you are moving around here. Then this becomes very small. Then this whole magnitude becomes very large. Okay, so when you are traveling along this half circle, then this magnitude of this one will be something like this. Okay, so this is the way of sketching the polar plot for the Nyquist analysis, and result is the result of the Nyquist analysis is if this trajectory encircles this point at least once, it has RHP poles same as the number of encircles. Okay, so for this case, you start out this and go around this and go around this, and you come back to the origin without crossing this. So there is no RHP 0 in this equation, so system is stable. Right? So that is the result of the Nyquist analysis, and that result is derived from the complex variable theory, conformal mapping theory, Cauchy's theory, Cauchy's theorem, and so on. Okay, very complicated. That's a complicated story, but result is this one. Okay, so this trajectory, this one, does not encircle this point, -1, 0 point, then there is no RHP loop in this characteristic equation. Okay, why we are worrying about this point? Because of this number 1. Okay, so 1 plus TMS equals 0, this number 1 is somehow reflected to this point. Okay, if you are interested in TMS equals 0, then you need to think about the encirclement of this point, origin. But because of this, you are considering this one. Okay, this is stable. Okay, all right. So you understand this. Okay, this is called Nyquist control, and this process calculating this in this manner is contour mapping, and the Nyquist contour encompass, it includes all the RHP plane of S-plane, Nyquist contour. Okay, so this system is stable. Okay, and there is another system. You increase this. Okay, you didn't change this numerator, denominator. You just increase this omega m prime 10 times, 100 times, something like that. That means phase remains the same because phase is not changing. By changing this constant, thing is just magnitude is increased, then this magnitude curve will be raised in parallel, in this way. Okay, then it starts from here, and there is omega p1 was here. So same omega p1 will occur here. So this is omega, figure is not correct. Okay, this corner is different, and the omega p2 was here. So you should have omega p2 here. Okay, omega p2 was here. So okay, that means this slope will be changed here, and it will, this was -1, and it will go down to -2, go down -3 here, and it crosses 0 dB somewhere here. Okay, at that time the phase is less than -180 degree, obviously. Okay, understand this. Okay, so assume somewhere here -270 degree, less than that. That means this was the original trajectory of this loop gain, and this is the increased with the increased gain, loop gain trajectory. So phase remain the same. Phase remain the same means the shape remains the same, and only this plot is expanding out, stretching out outside. So this will be something similar to this. It passes this -10 critical point. Okay, and do this again. Right. So that plot is here. This one, black one. So it goes like this, and this is a mirror image of this part, the previous part. And it will go around this and come back to this. Okay. So now you are trying to travel this contour. Then to reach this, you need to cut my finger once. And to get out of here, you need to cut this twice. Okay. That means there are two RHP roots in that equation, in the original characteristic equation. System is unstable, and it has this type of RHP pole, complex conjugate pole, one here, the other one here. Okay. I don't know what is this case. Probably, maybe another pole is necessary, even number pole is necessary, because if we encircles it, it encircles twice, and multiples of 2. Okay. Twice, 4 times, 6 times, something like that. All right, forget about that. Anyway, then Nyquist criterion is this equation. This is derived from the Cauchy's theorem. G is number of unstable RHP root in this characteristic equation. So there is at least one or more RHP root. That system is obviously unstable in the Beaver stability sense. So you need to understand the Beaver stability, but if you don't, that's okay. Okay, just the system is unstable, and the unstable system will oscillate. Okay, something like, okay, that is more than enough, right? And this G is number of RHP root in this characteristic equation, right? So this is the bad guys. So you should have 0 for this G, and N is the number of encirclement of this point. In previous example, this number is 2. Okay, and this P is the number of RHP poles in TMS. Okay, so TMS is this one. For this example, okay, there is no RH pole here. This is the common case. Okay, for the most system, there is no RH pole in TMS. If RH pole in the TMS, the system is was unstable originally. Open loop system is unstable, so we don't deal with that kind of system often. Okay, so but suppose you have a minus sign here, so there is one RHP pole here. That does not mean the system is unstable. Then you need to use number 1 here. Okay, only this equation changes. Okay, with that, if G is 0, system is stable. Okay, it's not directly related with stability of the system. What we are interested in, root of this one and this one, Tm as equals 0 is some equation, but we are not interested in that. Okay, and root of this and this, they are entirely different. 1 plus something equals 0, and something equals 0 is entirely different equation, because this is the rational function of S. Okay, it has a numerator, denominator. Then you should multiply denominator here. Then equation changes a lot. Okay, entirely different story. But for most cases, P is 0. Okay, usually P is 0. For the converters you will be dealing with in this semester, assume P equals 0. Okay, there are some special case. P is something else, 1, something like 2, or something like that. But there is very special case. For the most cases, P equals 0. And for your case, loop gain has this form. Okay, so loop gain is different form. There is no S here. You don't have this kind of trajectory of this polar. Okay, but always you have S in the denominator, because you want to have DC remain constant. Okay, for the DC regulation, S is coming here. So always you will have this type of trajectory. Right? Okay, so this is the result. If P is 0, then N is same as G. Okay. For the stability, number of RHP rule in TMS equals to 0 is same as number of encirclement of -10 made by the polar plot of loop gain. Okay. So in the previous topic, we concluded that if this polar plot pass through this line segment, system is stable. Okay. And it goes through this point is marginally stable, borderline between stability and instability. And if this one passes this line segment, system is unstable. Okay. Their result is the same as the Nyquist analysis in simplified version. All right. So because of this is good. Just checking out this point, this frequency point. At this frequency, phase becomes -180 degree. That means this polar plot is crossing the minus real axis. Then the phase will become -180. At that frequency, if magnitude is larger than 1, then this is 1. Then this part is larger than 1, and this part is smaller than 1, smaller than unity. Okay. So our practice determining the stability, this region is unstable and this region is stable. And when passing this point, marginally stable, and the marginally stable system has two imaginary axes here, okay, in complex conjugate form. We confirm that through the simple calculation. All right. So this is the simplified version of Nyquist analysis. So this is enough. Okay. So we derive this using the sinusoid disturbance, and when it returns, if the magnitude is larger than unity, smaller than unity, same as the unity, with the phase of -180 degree difference and blah blah blah. Okay, the same conclusion applies to here. Right? Let me explain the conditionally stable case. Conditionally stable case is this one. Assume this is conditionally stable system. Then this is a critical point. This is a unit circle and critical point. One example is this one. It goes like this. It crosses this and crosses here and go back like this. Okay. This is a conditionally stable system because the phase falls below -180, while the phase, the magnitude is larger than unity. That means the trajectory is in the outside of this unit circle and in the second quadrant. That is the defined as conditionally stable system. And let me give you another example. Another example will be like this. This one. Let me use another color, different color. Okay. Both of them are conditionally stable system. Okay. If you see until this part, but this system is stable, right? Because it does not encircle this critical point, and this system is unstable because it encircles this critical point. Okay. If you ignore the crossing point of this, and here you ignore this and this point, so you ignore the even number of crossing point of minus real axis outside the unit circle, and just to take a look at this point and this point. Then still same this criterion can be applied to determine stability. Okay, this is unstable system. This is a stable system, but they are conditionally stable or unstable. If the gain will be reduced, then something will be changed. Stability will be changed. Okay, but you don't meet this kind of cases often. Okay. Anyway, conditionally stable system or conditionally unstable system is the worst system. I told you that system is worse than unstable system. If you know the system is unstable, then you will fix the problem. For this conditionally stable system, it can be stable in some situation, and it will be unstable in some practical situation. You will meet in the theory practical operation of the system. Okay, so that is very bad. Okay, but still this story is applicable this system. Okay, so maybe it's ideal to understand the Nyquist stability criterion and you interpreted that result using the simplified analysis, sinusoidal response. Okay, but either way is okay. Okay, just to remember this. This is stable. This is unstable for most cases. Okay, RHP root here is not this case, not 1. Is 2 because of it goes around and you should encircle this. Okay, because we are talking about the mapping of this Nyquist control, which includes the whole RHP of S plane. So this becomes infinity. All right. So don't worry about evaluating this part. This S simplify your job. Okay, very trivial. Just concentrate on this part, then you judge the stability of the whole system. Okay, that is the Nyquist analysis on 1 plus Tm S equals 0. Another situation. Suppose you connected two systems, two converters, for example, and this is the output impedance of upstream converter, GO upstream. This is the input impedance of GID downstream. Okay. Suppose this converter is stable by itself. So this is individually stable and individually stable here. Then you connect two converters together. Then this is the input and this is the output of combined case. Okay, let me combine the case. Okay, and suppose this gain is A1 and this is the A2, right? So systems are individually stable. So this is stable. This is stable. Then the equation of cascade system is this one. So cascade gain of V1, V2 is A1 times A2 times there is a voltage division, loading effect, GIU plus GID, then GID in the numerator. Okay? So this is stable, so it does not have any RHP root in the characteristic equation, and it does not have any RH root in the characteristic equation. Then problem is this one. Okay? Then you modify this, divide numerator and the denominator by GID, then 1 plus GIU divided by GID. Okay? Then this will determine the stability. Okay? There are three terms. This is stable. This is stable. Then the problem is whether this plus 0. This denominator 1 plus GIU GID equals 0 has any RHP root is our interest. Okay, that determines the stability of entire system. Then this form is exactly same as this form. Then you directly apply the result of the Nyquist analysis and result of our analysis. So it can be considered as the loop gain. There is no loop here, no feedback loop. Okay, there is no apparent feedback mechanism, but still you can use this result of this and to determine the stability of this combined system. All right, that is one example. For that case, usually the loop gain is something like this. It starts out here and go back like this. Okay? Still, you can apply the Nyquist criterion under this strange shape loop gain. It really doesn't matter. The shape of loop gain. This is the typical example because of presence of this. Okay? So this is the very general things. In here, there is no feedback loop. But still, you can apply this. And this quantity, GIU divided by GID, can be considered as the equivalent loop gain of the system. Okay? So this is a very general tool to determine the stability of the feedback systems or stability of interconnected system. Okay? Each system is individually stable, but if you connect them together in strange manner, you don't know what will happen. Okay? So this issue is very important. Previously, people, they used only one standalone converter, one source, and one load. Now they are connecting everything together. Okay? They are talking about DC, power distribution system. Then many converters are interconnected, okay, in very complicated manner. Maybe some inverters, some other thing. Then there is a high risk of occurring this stability problem due to this between the system interaction. Right? So this is the one tool, a type of tools to determine the stability of the integrated system, very complicated system. There are many other techniques that is called EET, external element theorem, and there is another feedback theorem, circuit theorem called feedback theorem, and this one, like stability theorem. There are three critical techniques to analyze the stability performance or design approach to establish the design approach of complicated system. Right? Now we are studying the stability assessment of this standalone converter, and we spend some time on this lecture slide because the knowledge about this standalone converter will be the fundamental basics to explore dynamic performance and stability analysis and design optimization of complicated DC power distribution systems, which will be the subject of probably future lecture. Okay, now let's take a short break and we'll come back to finish up the remaining part of this lecture.